Okay, let's talk about multiple regression now that you have been through simple regression. I don't think you're going to find it too terribly difficult. One thing that I didn't do with simple regression was really talk to you about the model assumptions. And so here, going through multiple regression, one of the things you want to pay close attention to are our model assumptions and how we check those assumptions. All right, so let's talk about the general multiple regression equation. All right, I know for some of you with math phobia, this probably looks horrible, but basically is saying that we are predicting y from a bunch of x's. All right, and here in this model equation, we've got n x's, and on each of those x's, we have a slope denoted by the b. And the a is our intercept or constant term, just like it was in simple regression. All right, so a is the y-intercept, which is the value of y when all the x's equal 0. All right, and then each slope on each x is the amount by which y changes when that particular x increases by 1, but we hold all the other x's constant. So in other words, we're only moving one x at a time. All right. And one of the things that I'll talk about here in a minute is unstructured versus structured slope, unstandardized versus standardized slopes. And what I'm describing to you here with this B1 is what would be called an unstandardized slope. But we'll come back more to that once we get into JASP. All right, so what are our assumptions of running a regression model? All right, first is there is a linear relationship between the dependent variable and the set of independent variables. All right, so again, we assume linear increases or linear decreases. We are not taking into effect, like parabola relationships where something goes up and then down and exponential relationships. This is just linear. The variation in the residuals is the same for both large and small predicted values. All right, this is called homoscedasticity. All right, try saying that really fast. All right, so again, homoscedasticity. All right, the variation around the regression equation is the same for all values of the independent variables. All right, in other words, we don't get really big residuals or errors for large values of our x, but small values of x, we get really small residuals. All right, that would not be homoscedasticity. In other words, it's basically the same types of residuals all along our x values. All right, the residuals follow the normal distribution. So one of the common mistakes that you'll hear people say is that, oh, I can't run this ANOVA or I can't run this regression because my sample is not normal. That is not true. We don't need samples to be normal. And I've been mentioning this along the way in the class. What we need is for the residuals to follow a normal distribution, because when the residuals follow a normal distribution, we're able to back into the fact that most likely our population is normally distributed regardless of the shape of our sample. All right, so this is a big one. This is arguably the most important assumption. All right, the independent variables are not correlated. So when they are correlated, it is called multicollinearity, and we do not want them to be correlated, okay? And lastly, the residuals are independent. All right, so these are our assumptions, and I think you'll find at the end that they're pretty easy to check for. All right, so let's go through a JASP example here. In the data file, we have a sample of 20 homes. We would like to investigate which factors significantly predict the heating cost in the month of January at the 5% significance level. What are the independent variables? Okay, you may be looking at the data file right now, and if we want to predict cost would be our dependent variable, and then what remains is mean temperature outside, the number of inches of insulation in the attic, the age in years of the furnace, and whether or not the home has a garage. Now, unfortunately in JASP, we cannot use qualitative variables in our linear regressions. All right, so even though garage is coded 0, 1, it's not a continuous variable. It is definitely qualitative because a 1 stands for the word garage. So unfortunately, we cannot use this in JASP. All right, so methods for solving in JASP. All right, so we've got something called stepwise regression. And actually, when we go into JASP and we put in our dependent variable and we put in our independent variables, we'll see this little drop down, and it's defaulted on the word enter. And enter just means whatever x's you put in, JASP is going to run that multiple regression in one step, and you get all the p-values for all those variables. But the software has the capability of making decisions for you, because you know that if a p-value is greater than 0.05, we probably don't want that variable in our final model. And so we can ask JASP to make these decisions for us through either stepwise or backward elimination regression. So with stepwise regression, all right, it begins with a single independent variable. So we put in 1x. If the p-value is less than 5%, we leave it in the model. If the p-value is larger than 5%, we remove it. And then we add another independent variable, adding each one at a time. Either it stays in the model because it's significant, or we remove it because it is not significant. The one that I'm going to teach you and focus on is backward regression or backward elimination. And it begins with the entire set of independent variables in the model. So we throw everything in, and then we remove, or JASP removes, an independent variable one at a time. And it chooses the one with the largest p-value over 5%. So if one variable has a p-value of 0.6, and another one has a p-value of 0.08, it removes the variable with the 0.6 p-value because that's larger. And we continue until all the remaining independent variables in the model are significant. All right, running the analysis in JASP. All right, we are going to go to linear regression. All right, so we will move this over here. And here is our multiple regression data. All right, and so the response is cost. So we want to go to regression, linear regression. Our dependent variable is cost. We're going to add temperature, insulation, and age to our covariates. And be careful, it will let you add garage, but garage is 0, 1, so it doesn't really make sense to add our qualitative there. All right. Under enter, we are going to select backward elimination. Okay. But we need to go under options and change our p-value. Unfortunately, the removal alpha is set at 0.1, and we want that set at 0.05. All right. And then the last thing we want to do is make sure we're checking for our assumptions. So under statistics, we're going to check collinearity diagnostics. All right, so collinearity diagnostics. And under plots, we're going to check residuals versus predicted and the QQ plot. So we go under plots and we check residuals versus predicted and the QQ plot. All right. Now we're going to look at our model details. All right, so so I'm going to try to do split screen here. All right, so here's all of our results. All right, there's our two plots. We've got this collinearity diagnostics. We've got a coefficients table. We have an ANOVA, and we have a model summary. Looking at model summary or the ANOVA table or the coefficients table, we notice that the model ran with 2 iterations. All right, in the first iteration, all right, and we can look here in the coefficients table, everything was entered into the model, but if we scroll over, we see that age had a p-value of 0.148. So age is no good to us. It is not significant. And so JASP dropped it from the model and reran with only temperature and insulation. Since everything is significant in that second iteration, that is the final model. All right. We want to be able to write the final regression equation as a single equation. All right. And so one of the things you'll notice, and let's go back to our coefficients table here. So here we're going to be looking in the second iteration for all of our results. We have intercept, temperature, and insulation. And you notice in the first column we have unstandardized coefficients. And then over here we have standardized coefficients. So what's the difference? Because most software will give you both. And there's times when we want one over the other. All right. So unstandardized represents exactly what I told you in that first slide. It represents the amount by which y changes if we change the variable by 1, all right, while keeping the other variables constant. This is typically used with interpretation, all right? When we can interpret the slope, we want to use unstandardized. It's in the metric of the x, okay? Now, standardized. This is measured in units of standard deviation, meaning a value of 1.5 indicates that a change in one standard deviation in x results in a 1.5 standard deviation increase in y. Now, what's that used for? Sometimes we get more complicated regressions that become more difficult to interpret. And so what we do is we look at the standardized, which tells us the larger the standardized value in absolute value, tells us the more significant that particular variable to the equation. In other words, notice here that temperature has a -5, insulation has a -14. So you may think insulation matters more because -14 is a bigger number than -5 if we're thinking in absolute value. But we go over here to standardize and we see that temperature actually has a bigger standardized value, which means temperature is contributing more to the variation explained in cost. Temperature matters more in the equation, okay? But for writing our equation, our multiple regression equation, we're going to use the unstandardized coefficients. And so we get y equals the slope, and we can write our intercept value down, minus the slope on temperature times temperature, minus the slope on insulation times insulation. And this would be our final regression equation. All right, let's talk about interpreting the p-values. All right, so if we look in the ANOVA table, so let's go over here. So in ANOVA, and again, we're only looking at the second iteration because it's the only one that matters to us. We notice a p-value of less than 0.001 in this ANOVA table. Well, what does that p-value mean versus the p-values down here in the coefficients table? Well, the p-value in the ANOVA table is for a global test. All right, it says that the set of independent variables effectively estimate home heating costs. So as of right now, the set that we've put in, so temperature and insulation, effectively estimate heating cost. The p-values in the coefficients table tell you the significance of the individual variable that we're interested in. So less than 0.001 on temperature says temperature is significant in estimating the changes in heating cost, and the 0.008 for insulation says that insulation is significant in estimating heating costs. All right, so we talked a little bit about the coefficient of determination with simple regression, and we're going to stick with it again because it's so good in explaining what percent of the variation in our y is explained by our x's. So again, this gives us the percent of variation in the dependent variable explained by the set of independent variables. But there's a problem. And that is that r squared will continue to increase as we add more x's, all all right? It doesn't necessarily say that those added x's are good predictors of our y, okay? So r squared just keeps going up. Keep adding in x's. We could, in here, estimating heating costs, we could add in the thickness of fur of your dog, all right? So it's an x, and it's going to explain some of the variation in y, but obviously that's not a very good independent variable, all right? So for multiple regression, we want to interpret the adjusted coefficient of determination, all right? It's adjusted for the number of independent variables. So in other words, it incurs a penalty for the number of x's in the model. And so it's more accurate to use for the explained percent of total variation accounted for by the regression equation. All right, so let's go over here to our model summary. We're looking at our second iteration, and we're going over to our adjusted r squared, and we see that 74.9% of the variation in heating costs is explained by temperature and insulation, our two significant variables. All right, the last thing we want to do is check our assumptions. All right, so the first one we want to check is that we do not have multicollinearity. In other words, the x's are not correlated. All right, so what we're going to do is check the VIF. All right, and this is, and it stands for the variance inflation factor. And if you look in your coefficients table, you can scroll over and see a VIF from having added your collinearity diagnostics. And so for both temperature and insulation, we see a value of 1.011. Since these are less than 10, we assume no multicollinearity present. So yay, one assumption down. All right, the big one I mentioned was that the residuals follow a normal distribution. All right, this evidence comes from our QQ plot. All right, so let's scroll down to our QQ plot. All right, and we see this diagonal, this y equals x line, right through the middle here of our graph. And these dots you see are our standardized residuals. And what we want is for them to follow pretty close to this red diagonal line. We don't want to see a pattern. We don't want to see squigglies. And what we see here is that our residuals are pretty close to our line, right? We don't see any residual that's way off. And so here, this looks good. We can probably assume that we've got our residuals as normally distributed. All right, the other three, the homoscedasticity, all right, that the variables are pretty consistent, or the residuals are pretty consistent, the linear relationship between the dependent and the set of independents, and then the residuals being independent, all come from the residuals versus predicted values plot, all right? And what you're looking for in this plot is random scatter. Does it look like a Jackson Pollock painting? Does it look like somebody just threw a bunch of dots out there without any pattern to them? And the answer is yes. So because we see random scatter here, we can pretty much assume that we have our assumptions met of homoscedasticity, linear relationship between the dependent and set of independent variables, and that the residuals are independent.